Professor Loeb says that based on his calculations, it looks like 3I Atlas has been losing an extreme amount of mass, which could mean it's exploded into a dozen smaller pieces.
Hey everyone, welcome back to the channel. Right now, as you're watching this video, there's something passing through our solar system that has scientists absolutely baffled. An object from interstellar space that's breaking every single rule we know about comets, and we have less than 40 days to figure out what it really is before it vanishes forever into the cosmic void. Harvard astrophysicist Avi Loeb has run the numbers, and here's the problem: the math doesn't add up. This thing is either doing something that's naturally impossible, or we're looking at something humanity has never encountered before. On July 1st, 2025, Chile's Atlas Survey Telescope detected our third interstellar visitor in just 8 years. They called it 3I Atlas. And at first, astronomers thought they understood what they were dealing with. Just another comet passing through, right? But as observations continued, something became very clear: this visitor wasn't playing by the rules. Every calculation, every measurement, every image captured started painting a picture that defied explanation. And now, with telescopes locked onto this object, gathering data that will define what we know about it forever, scientists are racing against time. Because once 3I Atlas crosses beyond our detection range in January 2026, that's it. No second chances, no future studies. Whatever we learn in these next few weeks becomes the permanent record. The implications here are staggering. Either we're witnessing a natural phenomenon so extreme that it forces us to rewrite our understanding of physics, or interstellar space has been carrying something through the darkness that we never anticipated. And the window to determine which reality we're living in is collapsing fast. The telescopes are gathering data right now, and somewhere in those observations lies an answer that could change everything we thought we knew about what's out there in the space between stars. Before we dive deeper into this story, make sure you hit subscribe and turn on the bell so you don't miss the next video. Alright, back to it.
Carbon dioxide requires a surface area of an object that is 20 kilometers in diameter, much bigger than we estimated for the actual nucleus of 3I Atlas. This morning we have a report that the object got much brighter than expected, and moreover, the color of the object is bluer than the sun, and that's very surprising because usually when there is dust around an object, it should make it red.
Now here's where things get absolutely wild. This object started losing mass at rates that make no physical sense. In early August, astronomers measured the outgassing at around 330 kilograms per second. Significant, but not unprecedented for a comet approaching the sun. Then something extraordinary happened. By late October, as 3I Atlas reached its closest point to the sun, that rate had exploded to 2 million kilograms per second. Let that sink in for a moment. That's a 6,000-fold increase. We're talking about an object ejecting 2 million tons of material every single second at peak activity. Avi Loeb sat down and did the energy calculations, and this is where the paradox emerges. To produce this kind of mass loss through natural ice sublimation, you need surface area, a lot of it. The solar radiation hitting 3I Atlas at closest approach delivered about 700 joules per square meter per second. When you work backwards from the observed mass loss, calculating how much carbon dioxide and water ice would need to sublimate to match what telescopes were seeing, the math demands at least 617 square miles of absorbing surface area. That translates to a sphere at least 14.3 kilometers in diameter. Some calculations push it even higher, suggesting the object would need to be 20 kilometers across. But here's the problem that has everyone scratching their heads. When the Hubble Space Telescope imaged 3I Atlas in July 2025, just 3 weeks after discovery, it captured something very different. The actual nucleus measured roughly 1 to 2 kilometers maximum. That's it. Not 14 kilometers. Not 20 kilometers. Maybe 2 kilometers at the absolute most. You're looking at a 16-fold discrepancy, and you can't hide 14 kilometers of ice and rock from Hubble's optics. The only way to make the mathematics work, the only way to reconcile the energy balance with what was actually observed, is if 3I Atlas underwent catastrophic disintegration. We're talking about fragmentation into potentially millions of smaller pieces, each one presenting independent surface area to solar radiation. The collective thermal exposure across all those fragments would match the energy demands. The math forces this conclusion. But even that explanation starts falling apart when you look at what happened next. Because 3I Atlas wasn't just breaking apart, it was doing something no natural comet has ever been observed doing. As it approached the sun, the object started turning blue. Now, if you know anything about comets, you know this is completely backwards. When solar radiation heats a comet, dust particles get released and scatter sunlight across longer wavelengths. They glow yellowish white, sometimes even reddish. That's textbook cometary behavior, observed across every single cataloged comet in our solar system. But 3I Atlas shifted toward blue wavelengths during its approach. Blue. That suggests metallic compounds reflecting light in ways that standard icy nuclei simply don't. Imagine watching a snowball get closer to a fire, and instead of melting normally, it becomes shinier and more metallic looking. That doesn't happen in known natural processes. Then on November 9th, 2025, 11 days after its closest approach to the sun, two observers from the British Astronomical Association, Michael Butner and Frank Nebling, photographed something that transformed the entire investigation. They weren't looking at a diffuse debris cloud, the kind you'd expect from thermal breakup. Instead, they captured organized column-like jet structures, an anti-tail formation extending 950,000 kilometers toward the sun. Read that again, toward the sun. Solar wind dynamics push material outward, away from the sun. That's fundamental physics. Yet here was a structure extending nearly 1 million kilometers in the wrong direction. The primary outflow stretched 2.85 million kilometers in the opposing direction, approaching double the distance between Earth and the sun. Additional imaging resolved at least 7 distinct jets, and here's what made scientists stop cold. These jets displayed geometric organization, precise directional patterns, the kind of structural coherence that looks like material is being channeled rather than passively released. Debris fields from thermal stress should create randomized particle distributions, chaotic, scattered. But these jets showed patterns, as if something was directing the flow.
In order to get that much mass out of ice, we need a large surface area of an object, and it turns out that it's a surface area of an object that is at least 20 kilometers in diameter, much bigger than the original estimate for the size of the object. So that would mean for a natural comet that it was broken up into many pieces such that the surface area, the total amount of surface of these many pieces adds up to the amount of mass that we need to release.
And then came the measurements that nobody could explain away. 3I Atlas was accelerating. Not just moving through space on a predictable trajectory shaped by solar gravity, it was actively gaining speed beyond what gravity alone could account for. The object gained roughly 94 kilometers per day squared at its closest approach to the sun. It was already traveling beyond 150,000 miles per hour, and somehow it was accelerating further. Forces don't just materialize from nowhere in celestial mechanics. When objects move through space, we can calculate their trajectories with extraordinary precision based on gravitational influences. But 3I Atlas was deviating from those calculations. This is where Avi Loeb's controversial alternative framework enters the picture, and before anyone jumps to conclusions, understand what he's actually saying. He's not claiming proof of anything artificial. What he's doing is framing competing hypotheses with equal scientific rigor. If standard cometary outgassing cannot explain the organized jets, the sustained mass loss from what would have to be countless small fragments, and the geometric patterns captured in November's photography, then you have to consider other mechanisms. Advanced propulsion systems, if they existed, would achieve far higher exhaust velocities than sublimation processes. They'd require dramatically less propellant mass to produce the observed accelerations. And directional thruster arrays would create exactly the kind of columnated, geometrically organized jets that telescopes photographed. Now compare this visitor to the other interstellar objects we've detected. Oumuamua, discovered in 2017, displayed no sublimation signatures at all. It was an inert body, tumbling through the inner solar system without any gas release whatsoever. 2I Borisov, which passed through in 2019, conformed perfectly to standard cometary physics. Predictable outgassing, gradual thermal fragmentation, everything matching established models. But 3I Atlas occupies this impossible middle ground. It's undeniably comet-like in composition. Spectroscopy confirmed. Carbon dioxide envelopes. Water ice signatures. Yet it's displaying accelerations, mass loss dynamics, and jet organization unlike anything cataloged across natural comet populations. The iron-to-nickel proportions didn't match textbook profiles either. The molecular fingerprint looks skewed, like reading a passport where all the authentication stamps are correct but arranged in the wrong sequence. Right now, at this very moment, the most powerful telescopes humanity has ever built are locked onto 3I Atlas, and what they capture in these final weeks will determine the answer forever. December 19th, 2025 marks the closest Earth approach. Hubble and the James Webb Space Telescope are conducting intensive spectroscopic campaigns through late November and December. These aren't routine observations. This is humanity's only opportunity for high-resolution study of this object. By January 2026, 3I Atlas crosses beyond effective detection range permanently. Once it fades past that threshold, the window closes. No future missions can chase it down. No improved technology in 10 or 20 years will get another look. Every spectrum captured, every trajectory measurement recorded, every image resolved during these 6 weeks becomes the eternal observational record. Spring passage carries it beyond Jupiter's orbit and into the outer solar system, accelerating toward the galactic void. And here's what makes this moment so profound. An object born in another stellar system, potentially drifting through cosmic darkness for billions of years, entered our solar system precisely when Earth hosts the technology capable of studying it. Think about that timing. If 3I Atlas had arrived a century earlier, we wouldn't have had the instruments to detect it. A century later, and we might have better technology, but this specific object would be long gone. The statistical convergence is breathtaking. The data streaming in right now will answer whether those millions of fragments are natural cometary debris dispersing according to orbital mechanics, or whether they're components of something far stranger. The disintegration is real, photographed, measured, quantified across multiple independent observatories. The jets are real, documented with precision. The acceleration defying pure gravitational models has been calculated. What physical processes created these phenomena will define not just what 3I Atlas is, but what the darkness between stars might be carrying. Either we're expanding our understanding of natural physics in ways we never anticipated, or interstellar space contains objects that current science doesn't account for. Both conclusions are profound. Both would change how we view the cosmos. And somewhere in the spectroscopy data, in the trajectory calculations, in the thermal models being analyzed right now, lies the answer. The telescopes aren't looking away. The data is accumulating. And very soon, we'll know what just passed through our cosmic neighborhood during humanity's first moment, capable of truly recognizing what we're seeing.